we have a finite semigroup in which both the cancellations hold, then it is a group. This video is continuation of part 2 of key concepts to understand groups. In part 2, I discussed the notion of identity element and the invertibility of an element. Consequently, the notion of monoid was defined. Link of that video is in the I button. Today, we begin our discussion with the definition of groups. A monoid G composition is said to be a group if every element of G is invertible. In other words, a non-empty set G with respect to a binary operation composition is said to be a group if it satisfies the following three criteria. Number 1, this composition has to be associative, that is A compose B compose C equals A compose B compose C for all ABC in G. Then identity element must exist in the group, that is there exists an element E in G such that A compose E equals C compose A equals A for all A in G. And finally, inverse of every element exists. That is, for each A in G, there exists another element B in G such that A compose B equals B compose A is the identity element. So, when these three criteria hold along with a binary operation on a non-empty set, we call that set to be a group. A group G composition is said to be an abelian group or a commutative group if the ambient operation, that is this composition, is commutative binary operation. Okay, and that is to mean that A compose B equals B compose A for all AB in G. If this holds, then we call that group to be an abelian group. Now we'll see some examples of groups. One can check that this monoid Z plus is in fact a group because for any element A in Z, minus A is the inverse, and therefore every element in this monoid is invertible, and hence it is a group. And moreover, this addition operation is commutative on this set, and therefore it is an abelian group. Similarly, Q plus is an abelian group, and if you exclude 0 from these rational numbers, and then this set forms a group under the multiplication operation, and all of them are examples of infinite abelian groups. And if we want to have finite abelian groups, then we can take the nth root of unity under multiplication. For example, plus minus 1, that is the square root of unity under multiplication, that forms a group. Similarly, 1 omega omega square, that is where omega is a primitive cube root of unity, and that also forms a group under multiplication. Similarly, here I is the primitive fourth root of unity under multiplication. That set fourth roots of unity will give you a group structure. Alright, but the next example will give us a more general class of example. For any non-empty set A, we denote SA to be the set of all bijections of A onto itself. Then this SA forms a group under composition of functions. And this SA, what we call the symmetry group on the set A. And we will see in the subsequent classes that any group can be embedded in a symmetry group, and that's due to Cayley's theorem. Anyways, and one can easily check that when this set A has at least 3 elements, then this group SA is non-abelian. Now we'll see an interesting property of a groupoid. Now we see cancellation laws in a groupoid G. So there are two types of cancellation, from left and from right. Accordingly, we have left cancellation and right cancellation. So what is left cancellation? So when we have an expression like this, A compose B equals A compose C, that would imply B equals C. That means we can cancel A from the left of both this expression, and that implication is what we call left cancellation. Similarly, likewise, when you can cancel expression elements from the right of some equality, we call that implication to be right cancellation. Now we will see that this doesn't hold in general. In any groupoid, this is not necessarily a true. For example, you take the groupoid set of integers with respect to multiplication, then certainly 0 times 1 equals 0 times 2, both of them are equal to 0, but this does not imply 1 equal to 2. I mean, 1 is certainly not equal to 2. So here left cancellation doesn't hold. Similarly, right cancellation doesn't hold because this operation is commutative. So in general, cancellation doesn't hold in a groupoid. Now we'll see that this cancellation holds in any group. To see this, consider a group G composition and elements A, B, C in G such that A composition B equals A composition C. Now since G is a group, every element is invertible, therefore A inverse exists. So now we can decompose both of them with A inverse, so as to obtain A inverse compose A compose B equals A inverse compose A compose C. Now with the help of associative property, that will become A inverse compose A compose B equals A inverse compose A compose C, but that is your identity. So identity compose B equals identity compose C, and that would mean B equals C. So you started from here, A compose B equals A compose C, and that would mean B equals C. That means from left A is being cancelled, and therefore left cancellation holds in this group. Similarly, right cancellation also holds in any group G. Now let us try to reformulate this cancellation laws in terms of properties of functions from G into itself. Let me make it explicit. So let's consider any groupoid G composition. So consider groupoid G composition and take any element and let A belongs to that groupoid G. Then given that element A in G, we can construct two functions. Let's call them LA. So L stands for the left multiplication by the element A. So it from G to G, and the rule is that X is being mapped to A compose X. So we define LA, and likewise RA. So R stands for right multiplication with respect to the subscript A, X being mapped to X compose A. Okay. So of course it is a groupoid, so this map is all defined. Indeed, this is an element of G. Now let us try to see what is the connection between this function and left cancellation. Now you can note that LA, I am saying that left cancellation holds if and only this LA is injective for all A in G. Indeed, because LA x equals LA y would have to imply x equal to y in order LA to be injective function, right? So what is the meaning of that? LAx equals LAy, that means A compose x equals A compose y, and you want LA to be injective, that means you want x to be equal to y, and that is exactly the requirement for the left cancellation law, and that's why we can say that so left cancellation holds if and only this function LA is injective, LA is 1 1 for all A belongs to G. Likewise, right cancellation holds if and only these functions RA are injective for all A belongs to G. Okay, now we'll see a sort of converse of this theorem, that given a structure with this cancellation property, this becomes a group. So let us see them now. So let us try to prove this result now. A finite monoid with one of the cancellation laws, let's say left cancellation, is a group. So let us try to see how can you prove it. So it's already given a monoid, and then we have to establish that it is a group. That means all you need to prove that every element in this monoid is invertible element, right? So let's consider. So let G be a finite monoid, and we pick an element A in G. Okay, we want to prove that A is invertible. Alright, now since we are assuming that left cancellation holds, that means from our previous discussion we can say that left multiplication map LA is injective. So then LA G to G, so given by X being mapped to AX or A compose X is injective. Alright, now G is a finite set, it's a finite monoid, and therefore every injective function is surjective. For a proof of this fact, you might check the I button. There is a link of my previous video where I have shown this result. So since G is finite, LA is surjective. As well. Alright, so what does that mean? That means every element in G has a preimage under this function. So in particular, since it is a monoid, identity element exists in G, so that identity element also has a preimage under this function, right? That means there exists an element B in G such that LA of B equals identity, which means A composition B equals identity. Alright, but left cancellation means all the left multiplication maps are injective. So in particular, corresponding to B there is also a left multiplication map. Let's we denote this by L subscript B. That function is also injective from G to G. So that is also surjective because G is still finite, and therefore there exists an element C in G Okay, so similarly, there exists C in G such that B compose C is identity as well. Now things are around B, so by associative property, we have A compose B compose C equals A compose B compose C. That would mean A compose identity, that is A, equals identity compose C, that is C. So that means A and C are equal. So we can replace this C by A so as to obtain this. So A compose B equals B compose A equals identity, which means B is the inverse of A and therefore A is invertible. So in this monoid, every element is invertible and therefore this monoid becomes a group. Now we'll see another question like this. So now we have a finite semigroup in which both the cancellations hold, then it is a group. So there is a slight difference from the previous problem. So in the previous problem it was a monoid, so we have the identity element, but we have one less cancellation. Now we have both the cancellation but we don't have the identity element. So basically we somehow we can manage to show that this semigroup has the identity element, then we are done, because then it becomes a monoid and having cancellation property, and then rest follows from the previous problem. So this is our aim, that we will show that this semigroup contains the identity element. Okay. Alright, so this is keeping this in our mind. So what we can do, so just like before, so it's a finite semigroup. So let G be a finite semigroup, and you pick an element small a from G. All right, so with this both these cancellations, so we know that this left and right multiplication maps, all of them are injective from G to G. Ax is 1 1 is 1 1, and since G is finite, LA is on 2, and therefore there is an element, there exists an element. Okay, so there is a pre-image, there is a pre-image of the element A, because A is also an element, is itself an element of G. So there is something from G maps to A, right? And that element is desirable to the identity element. So let us denote this by E. So then there exists an element E in G such that LA of E equals A, which amounts to say that AE equals to A. So now we wish to show that this E is actually the identity element for the semigroup, which means we want to prove that X compose E equals E compose X equals X for all X in G. So now we wish to show that E is the identity element in G. All right, so we pick an element, let's say small x in G. So we fix it arbitrarily. So let small x belongs to G. So you want to show that x e equals E, x equals to x. All right, now let's make use of this injectivity of LA. Okay, so what do I mean? So what is this? So note that what is this element? LA of Ex equals, so by the defining property of LA, it is A times Ex, again by associative property X, but AE is same as A, so this is Ax, and that means LA of X, which means LA of Ex is same as LA of X, but LA is injective, and therefore that would imply this Ex equals X. Ex equals X. Okay, so let's give it equation A. Now we have to prove the other way, that is Xe equals X, right? For this we have to take help of the right cancellation. For example, we know that this right cancellation Rx, I mean that right multiplication map is also injective due to right cancellation, right? So G to G, small g is being sent to that Gx is 1 to 1. Again, since G is finite, Rx surjective as well. And okay, now let's see. We don't have to use this surjectivity. I think injectivity is enough. What is this quantity if we apply Rx on Xe? So this quantity means this will become X E X, and then by associativity Ex, right? But this Ex is same as X, so it is X times X, which means this is Rx on X. So Rx of X equals Rx of X. So since Rx is injective, that would imply Xe equals X. So let's denote this equation by B. So from A and B, we have Xc equals Ex equals X, and since X is arbitrarily chosen, this holds for all X in G. And therefore, this semigroup has the identity element, and therefore it becomes a monoid, and rest follows from the previous problem. Now, before I conclude today's session, I just want to see another problem along the lines of these cancellation things. So here it comes. Let G be a semigroup in which both the cancellations hold. Then given for every element A in G, this set a to the power n, where n varies over all positive integers, is a finite set. Then G is a group. Now if you compare with the previous problem, in the previous problem it was given that it was finite semigroup. Now it is allowed to be infinite semigroup, but for any element A that all positive integer powers, that is a finite set. Okay. So let us see how can he prove it is a group. It is given semigroup. So basically we need to prove that it has an identity element and every element is invertible, right? Okay, so let's try to guess the identity element. So before that, let us fix some element A from that semigroup G composition. So we fix A from this G. Now the given that then these elements a square, a cube, that all positive integral power of A cannot be all distinct, right? Because it is only a finite set. So which means there must be two indices. Let's say, so there exist two indices mn such that a to the power m equals a to the power n, such that a to the power m equals a to the power n. Moreover, we can make the distance of m and n arbitrarily large. So what do I mean? Let's say in the worst scenario, let's say a to the power 5 equals a to the power 6. Then we can make it equal to a to the power 7. We can compose a with both of them, and then we'll have a to the power 6 equals a to the power 7, so on a to the power 8 dot dot dot. So we can take any large m, large a to the power large m and smaller value of n. So we can make this distance large as you want to be, as one want to be. So we can make this m slightly more larger than n. So as per our requirement, we just need to have where m minus n, we just want to have greater equals to. All right. Then we denote the element a to the power m minus n to be the desired identity element. We guess that that could be an identity element, or the identity element for this structure. So we denote this element by E, a to the power m minus n, and this is indeed an element of S because S is semigroup and m minus n is a positive integer. All right, so now we wish to prove that this E is actually an identity element, and then we'll take help of these cancellations. All right, so basically we want to prove that Ex equals Xc equals X for all X in G. All right, so what we can do, consider an element X in G, then what is this value? Let's say L a to the power n, because we know that left multiplication maps and right multiplication maps are all injective because of these cancellation laws. So what is this quantity L a to the power n of let's say ex? So that would mean, so left multiplication by a power n, so a to the power n ex, which means after associativity a to the power n compose a to the power m minus n times x, well, compose x, or maybe we should not put the compose anywhere. This means composition of a n times, this means composition of a m minus n times, so altogether composition of a m times, so this is a to the power mx. So this is a to the power mx, and a to the power m is same as a to the power n, and therefore this is equal to a to the power nx, which means this is this, right? Now let's use that this function is injective, so ex must be equal to x. So this should imply ex equals x, right? Similarly, we can think about Ra to the power n of xe, and that would give us Ra to the power n x by similar kind of argument computation, and then that would mean x equals x. So from these two we can say that E is the identity element. So let's call it to be 1. So from 1 and 2 E is the identity element in the semigroup G. So it becomes a monoid now. Now we need to prove that every element is invertible. So let's pick an arbitrary element, let's say B. So let B belongs to G. So all you want to show that inverse of B exists in the monoid G. So by similar kind of argument, there exist integer R and S, positive integers R and S, such that b to the power R equals b to the power S. Also the distance between S minus R or R minus S, let's say R minus S is at least 2. And similar argument, by similar kind of argument, we could have proved that b to the power R minus S is also an identity element for this semigroup. But we know once the identity element exists, it exists uniquely, and therefore this element b to the power R minus S must be equal to this identity element E. So then b to the power R minus S must be the identity element E. Now R minus S is at least 2, so we can extract 1b out of this, because presumably it is a semigroup, so only positive integral power of an element is defined. Now it is a monoid, so so we can extend it to 0. We can define power of a till non-negative integers, that much only. So b to the power R minus S equals E would imply b times b to the power R minus S minus 1, which is equals to identity, but we can also write it like that, b equals to identity, which means this element b to the power R minus S minus 1, which is positive integer, is an element of G, is the inverse of B, and therefore, and since B is arbitrary element, every element in G is invertible, and hence it is a group. Okay, so that's all for today. Thank you for watching this video. See you next time.